Hello friends, welcome back to another session of dbms. Today I'm going to discuss BPlusTrees and how a BPlusTree is used in dbms for indexing. A BPlusTree is a self-balancing MV search tree that maintains sorted order and allows efficient search, insert, delete, and range queries. So it is widely used in database indexing and file systems due to efficient disk access patterns. So what's the structure of a B plus tree? Plus tree will be having a root node, internal node, and then a leaf node. So a root node can be a leaf node as well, and otherwise it acts as an index node to direct searches. Internal node contains only keys and act as decision points for traversals, whether to take the left subtree or the right subtree. So each key in an internal node separates two children subtrees, and then leaf node stores actual data values. Okay, so linked together for efficient range searching. Every leaf node is at the same depth, ensuring order of log and time complexity for operations. And internal nodes store only keys and act as navigation pointers. And leaf node contains actual data records and then multi-way tree. Okay, so each internal node can have up to m children. A node can store up to m minus 1 keys. And the B plus tree is designed to minimize disk IO operations by reducing the height of the tree. The linked leaf nodes allow fast range queries and order traversal. The operations that you can perform on a B plus tree are search operation, insertion operation, deletion, and range queries. Search operation takes order of log n, and then insertion also takes logarithmic time, and deletion also takes logarithmic time. And range queries take logarithmic time plus order of k. So how is the search operation done? Start from the root and traverse down using the keys, and we compare the keys and take the direction where it is greater than or less than the value that we want to search. Once at the leaf node, perform a binary or linear search for the key. And then you also will be retrieving the disk addresses pointing to the full tuple. And then insertion operation. So insert in the appropriate leaf node. If the node overflows, then we are splitting the node and pushing the middle key, which is the median, to the top node. Okay. So that's what we'll be doing. So a deletion operation, we remove the key from the leaf node, and if the node underflows, like there is a formula or the property of the B plus tree where there will be a minimum number of keys as well in the node. Okay, so the minimum number of keys will be m by 2 seal. Okay, so if it is lesser than the minimum number of keys, then we have to borrow a key from the neighboring sibling or merge with the sibling and adjust parent pointers. So this is for the delete operation. And coming to the range queries, we start from the first key in the range and follow the linked leaf nodes until the end of the range. So this is what we'll be doing for each and every operation on a B plus tree. So these are all the differences between the B tree and the B plus tree. So coming to the data storage. So in B tree, the data is stored in the internal nodes as well as the leaf nodes. But coming to the B plus trees, the data is stored only in the leaf nodes. Okay. And the internal nodes will be only like pointers leading to the leaf node. And then coming to the leaf node linking, so there won't be any linking in the B trees for the for the leaf nodes, but in the B plus tree, the leaf nodes will be linked for the faster range query. Okay. And then the range queries are slow in B trees, okay, because it has to traverse the entire tree. And then in B plus tree, it is fast because there is a linked list traversal in the leaf nodes. All the leaf nodes are connected in a linked list, okay. Preferably, it is a doubly linked list. So all the nodes are connected in a doubly linked list. So search performance is order of log n in B tree. And then in the B plus tree, the search performance is order of log n, but more cache friendly. So the real world applications are database indexing. So where Oracle uses B plus trees for indexing, I have shown this as a lab experiment. So if you want, I'll be giving you the link of that lab experiment in the iCard. So you can see that practically, how a B plus tree is used for indexing in Oracle. Okay. So let us see. how many maximum number of keys and the minimum number of keys a B plus tree of order m will be having. So for the internal node, so the max keys will be m minus 1 and the minimum keys will be ceil of m by 2 minus 1. For the leaf node, it will be m minus 1. So the max keys will be m minus 1 and the minimum keys will be m minus 1 by 2 whole ceil. Okay. And then for the root node, if internal, then there will be m minus 1. And for the root node, there won't be any condition for the minimum number of keys. It can also have one children and one element in it and so on. So for say, for example, the B plus tree is of order M, which is equal to 5. So order 5 B plus tree. What will be the minimum keys for the internal node? So the minimum keys will be 2 and the minimum keys for the leaf node will be 2. Okay. So the maximum keys will be M minus 1, which is 4 and the maximum children will be 5. Okay. Right. So I'll be showing you how to construct a B plus tree for the following data. So this is a sailor's table. So the sailor's table is having SID, the name of the sailor, and then the rating, and then the age of the sailor. So here you can see this is the SID. SID is the primary key. So these are all the data in the primary key. So you can see that the data is unique over here and it is not null. So we'll be constructing a B plus tree for the SID and for the primary key, Oracle automatically constructs a B plus tree. But if you specifically want to create an index for some other attributes over here, you can also do that. As I already told you, I have created a video for creating an index, creating explicit indexing. So you can watch that video. And this is where your Oracle itself will create a implicit indexing B plus tree for the primary key. Okay, so SID is the primary key and we'll see how that B plus tree is constructed. So let us create a B plus tree for the sailors table where SID is the primary key in the sailors table and the values in the B plus tree will be the SIDs from the sailors table. Okay, so we'll try to create it that way. And as you can see, like we have the order of the B plus tree, M is equal to 5. So what does that mean is that, so when you have a B plus tree of order 5, it means that you will be having the maximum number of children as 5 and the maximum number of keys in the node will be M minus 1, which is 4. Okay, so this is the node structure and we'll try to insert the keys into the node. Okay, so the first key is 8. So 8 is put in the tree and then next is 11. 11 is checked against 8. 8 is lesser than 11. So 11 comes after 8. So you will have to see to it that the order inside the node, the element order inside the node should be in ascending order. Okay. Next element is 2. 2 is lesser than 11 and also 8. So we need to insert 2 here. So 2, so 2, 8, 11. And then we have 24. 24 comes as the last element inside the node. Okay, fine. So the node is fine, but when we try to insert the next element, then there will be a problem. Okay, so because that is an overflow condition. So what will be the order of the elements? So the order of elements will be 2, 6, 8, 11 and 24. So we'll imagine that we have already inserted the element and now we'll try to find the median. Okay, so the median of this is 8, right? So we have to split the node and we have to construct the tree from bottom to root. Okay, so the tree always goes from the bottom from the leaf node to the, okay. So now we are splitting. So what will happen? 8 will go on to the top and 8 will have the left child which will be having elements as 2 and 6. And on the right side, like 8 will be having 11 and 24. Okay. Not only this, we have to remember one of the important B plus tree properties, which is that all the data will be in the leaf node itself. The internal nodes will be like pointers. So 8 also will be on the right side. Okay. So as you observe that whatever elements will be there on the left side will be lesser than the root and the elements on the right side will be greater than or equal to the root. Okay, so and also the root node element also will be included in it. So 8, 11 and 24 will be on the right side. So what's the next element? So the next element is 16. So where do 16 go? 16 is greater than 8. So this is how we are navigating to the leaf. So 16 is greater than 8. So it comes onto the right side and then it is inserted in ascending order. So 16 comes here in between 11 and 25. So we have to insert 16 over here. So 8, 11, 16, and 24 will be on the right side. The node is fine because the maximum number of keys in the node will be m minus 1, which is 4. So there are 4 elements in the node. So the node is good. Okay. So we'll try to insert the next element. So the next element is 18. So 18 is greater than 8, right? So it comes onto the right side. So what will be the order of the element? So it will be 8, 11, 16, and then 18, and then 24. Okay. So there are five values in the node, so which is an overflow condition. So since there is an overflow condition, what we need to do, we need to take the median, which is 16, and 16 will go to the root node. Okay, so 16 will go to the root node. So let me show you that. So what will happen? 16 will go onto the root, right? So once 16 goes onto the root, then again it will get a right child, so which will be having 16 and also 18 and then 24. So I'll draw it neatly and show it to you. This is how the leaf nodes will look like. So we'll take the next element. So the next element is 10. So 10 is greater than 8 but less than 16. So it comes onto this particular node. Okay. And 10 is inserted in order. So since this is greater than 8 and less than 11, so it comes in between. So 8, 10, and 11. So since the node is having enough elements, so there is no need to split because there is no overflow condition. So the next element is taken. So the next element is 12. So where do 12 go? So 12 is greater than 8 and less than 16. So 12 comes here in the same node. Okay. So it will be 8, 10, 11, and 12. So since there can be the maximum number of values in the node can be 4. So yes, this is having 4 elements. So there is no overflow condition. So we'll take the next SID. So the next SID is 40. So 40 is greater than 16. So what happens? It comes onto the this node. Okay, so 40 is inserted here in order. So which is greater than 24. So it is inserted after 24. Okay, so there is no overflow condition. So the tree is good. So we'll take the next element, which is 36. 36 is greater than 16. So it comes into this node. So what's the order? So the order is 16, 18, 24, and then we have 36 and then 40. Okay. So this is the data that we'll be having in this particular node. So since there is a overflow condition, because the maximum value should be 4, but there are 5 values here. So the median is taken. So the median is 24 and 24 is taken to the root. So what will be there at the root? So I'll be having 8, 16, and also we'll have one more element, which is 24. And then the data is splitted like this. Okay, so I'll have 24 and then 36 and then 40 here. Okay, so 24, 36, and 40 as the right child of 20. Okay, right. Again, after this split and moving up of 24 median onto the root, we have to check whether this node is having is overflowed or not. Okay, so this node is not overflowing because there can be 4 elements. There are 3 elements. Okay, this is fine. Okay, right. So this is how the B plus tree looks like. So we'll take the next element. So the next element is 9. So 9 is greater than 8 and less than 16. So 9 comes over here in this particular part. So where the order will be 8, 9, 10, 11, and 12. So since there is a overflow condition, 10 will go on the root. Okay, fine. So what will happen? 10 will come here in order. So it will be 8, 10, 16, and 24 at the root, and there is no overflow condition at the root. So there can be 4 elements. So 4 elements will be there at the root. So there is no further splitting needed here at this particular root. Okay. So this is how the B plus tree looks right now after inserting 9. So we'll try to insert 41. So where do 41 go? So 41 will be greater than 24. So it will come onto the right subtree of 24. So 41 will come here. So since there is no overflow condition, there can be 4 elements in the node. So 41 fits in here. Okay, so no need of splitting and all that. So we'll see what is the next element. So the next element is 26. So we'll see where it fits in. So 26 is greater than 24. So it comes onto this side. So if you just take the order of this, so it will be 24, 26, 36, 40, and 41. So this will be the order of the elements in this particular node. But since there is a overflow condition, so 36 is the median. So what we need to do, just push 36 onto the root. Okay. So 36 will go onto the root like this, and 36 will have a right child, which will be having 36. So which will be having 36 and 40 and 41. Okay, so 40 and 41. And so we won't be having 36, 40, and 41. So we'll be having 26 here. Okay. So this is how it has gone onto the root. Okay. So there is a split in the leaf node. But if you just observe like the node at the root right now, so there is a overflow condition. Okay. There can be max of 4 elements in the node, but there are 5 elements in here. Okay. So we need to now split this particular node, take the median and then split. So what is the median here? 16 is the median. So 16 will go on to the root, and then its left child will be having 8 and 10, and the right child will be having 16, 24, and then 36. So this is how the root node looks like. So 16 goes onto the top, and then it will be having 8, 10 as its left node, and then 16, 24, and 36 as its right node. And then these are all the leaf nodes. So this is how it's split. But as you observe, like each and every node will be having the elements in sorted order. But how do the data at the leaf nodes will be stored? So say, for example, 2 is the SID of a particular sailor. So when I find 2, okay, so first thing is I'll try to see whether 2 is existing or not. Yes, in the index I found 2. Okay, and the navigation no, to finding whether 2 is there or not is very easy. We'll try to see whether 2 is less than 16 or greater than 16. So 2 is less than 16. So I'll come on to this direction, and then I'll search whether in this particular elements, I'll be searching whether 2 is less than 8 or greater than 8. So 2 is less than 8, so I come on to this side. So finally in the leaf node, I found 2, right? So what will be there at the leaf node? Okay, so at the leaf node, so after finding 2, now I would like to get like where, what is the address? Okay, so the disk address pointing to the full tuple I'll be getting here. So for 2, I'll be having some disk address, which could be like 0xA1 and so on. For 6, it could be like 0xA2 and so on. So what is all this? So this is the disk addresses pointing to the full tuple. So when I find 2, or what I'll do is I'll take this address. So this is the disk address, and I can directly go onto the disk and find the tuple. Okay. And also I can see whether a particular SID exists or not. So say, for example, I want to know whether 32 is there. Okay. So 32 SID is there. So I'll start at the root node. So 32 is greater than 16. So I come in this direction onto the right child, and then see whether this is internal node. So again, I'll compare. So it is greater than 24, but less than 36. So this pointer I'll be taking, I'll be navigating in this direction. And then I'll come to the leaf node and see that 32, so 24 is there and 26 is there, but there is no 32 here. So from this, I'll be knowing that SID 32 do not exist. Okay, so I'll be able to navigate or find out whether the sailor exists or not. And also I'll be able to do the I'll be able to retrieve the tuple in a very faster way rather than doing a full table scan. I hope you understood BPlusTrees. If you find this video helpful, like, share, and subscribe and comment. Thank you for watching.